Welcome to the Final Wager's Guide to Game Theory. Today, we're finally going to resolve a cliffhanger by looking at mixed strategy Nash equilibria. We return to the concept of minimax, which we discussed in a previous installment. Minimax is used to find your optimal approach in a zero-sum game by minimizing your opponent's maximum return, or by maximizing your minimum return. We've already looked at sequential games like chess. Here, we're going to look at simultaneous games like Final Jeopardy wagering. We solve for the optimal approach by using a probability distribution. There are two main types of Nash equilibria. Think of what we saw in the prisoner's dilemma. Each player will always confess. This is called pure strategy. You do the same thing every time. The second is called mixed strategy, where you randomly choose from among your options with a predetermined probability. Between pure and mixed strategies, every game has a Nash equilibrium. We'll come back to our favorite wagering scenario, where the leader has 20,000 and the trailer 14,000. Each player has two wagering ranges, small and large. Calculating the mixed strategy Nash equilibrium is a three-step process. Things are about to get algebraic. First, we'll assign a variable to each of our opponent's decisions. We return to the payoff matrix. On the left, we'll come up with some variables. Let's call the probability that the leader wagers small y. Since the leader must pick one or the other, the probability of these two must sum to 1. Therefore, we represent the probability that he wagers large as 1 minus y. We do the same with x for the trailer. Step 2. Determine your payoffs for each of your opponent's decisions. Let's look at it from the trailer's perspective to see how he should wager. We start with when the trailer goes small, 0. If the leader wagers 0, the trailer's payoff will be -4. We multiply that by the probability the leader wagers 0, y. If the leader instead wagers large, the trailer's expected payoff will be 0. We multiply that by the probability of the leader's large wager, 1 minus y. When the trailer wagers 0, therefore, he expects his payoff to be -4y plus 0 times the quantity 1 minus y. We do the same thing with the trailer's large wager. His expected payoff will be 0 times y for when the leader wagers small, plus -2 times the quantity 1 minus y for when the leader wagers large. Still with me? Okay, good. Our final step is to set the two formulas equal to each other. We'll walk through the algebra together. First, we eliminate the payoffs with 0. We're left with -4y equals -2 times the quantity 1 minus y. Let's multiply both sides by -1 to make things easier. 4y equals 2 times the quantity 1 minus y. On the right side, let's distribute that 2 into the quantity 1 minus y. That gives us 2 minus 2y. We'll add 2y to both sides of the equation to remove it from the right half. Now we're left with 6y equals 2. Let's get the y by itself. To do that, we divide both sides by 6. We're left with y equals 2 over 6. This equation reduces to 1/3. So y, the probability that the leader will wager small, is 1/3. You can do the math on your own, but take my word for it that since this is a symmetrical game, the probability that the trailer will wager small is also 1/3. We now return to our matrix with the probabilities put in. Remember, the probabilities for a given player's choices must add for 1. So if there's a 1/3 probability a player will wager small, there must be a 2/3 probability he will wager large. Now, to solve this, we need to calculate expected value, or EV. If you're unfamiliar with this concept, have a look at the associated video. When both players play the optimal mixed strategy, the leader will expect to win 2/3 of the time, and the trailer 1/3 of the time. Now let's see what happens if one player deviates from the optimal strategy. If the trailer maintains his mixed strategy, and the leader only wagers large, we calculate the probability of each happening, and sum the totals to find the expected value for each player. Again, it turns out to be 2/3 for the leader, 1/3 for the trailer. The same is true when the leader always wagers large, when the trailer always wagers small, and when the trailer always wagers large. Let's return one last time to our matrix, and add a new column and a new row for our mixed strategies. In any case, when either player uses the mixed strategy, the leader can expect to win 67% of the time, and the trailer can expect to win 33% of the time. Let's draw in the arrows to show how this works. Same as before. If we follow the blue arrows around the outside of the matrix, we enter an endless pattern. But see what happens when we highlight the middle cell, where both players choose the mixed strategy. Neither player can do better by unilaterally changing his choice. Therefore, both players playing a mixed strategy is a Nash equilibrium, which we call, fittingly, a mixed strategy Nash equilibrium. How does one choose randomly? I like to use the second hand on my watch. If it's a multiple of 3, I pick the small wager. Otherwise, I'll pick the large wager. Poker players do this sometimes when they want to randomize their play. It's a neat little trick, and we'll learn more about neat little tricks in future installments of the Final Wager.